So now that we've been finding some antiderivatives, it's only natural to start to solve some applications of these antiderivatives and indefinite integrals. So one of the things we can do is we can solve an initial value problem. And you can see I have a couple of them listed here. When you solve an initial value problem, you are actually finding the specific f of x that has this derivative and fulfills this condition, that it goes through the point 1 comma 3. Remember that when we find a general antiderivative or an indefinite integral, what we're finding is a whole bunch of functions that are essentially parallel to each other. They all have the same derivative, but they differ by a constant, meaning that they differ on where they are along the y-axis, right? And there's an infinite number of those bad boys. If you want to find the specific one that goes through the point 1, 3, it takes a little bit of extra work. Not much. Okay, so what I'm going to do is I'm going to try this number 51, which we happen to do in class, and I'm going to solve that for you so you can see how this works. So we have this derivative, f prime of x equals 2x plus 1. And you go ahead and do your antiderivative just like you did in our previous lessons recently. And so the antiderivative for 2x is, it's going to be x squared, but the reason it's x squared is it's 2 times x squared over 2, so that's x squared. The antiderivative for the constant 1 is just x, and then remember we stick that plus c on the end to represent all those possible functions that differ by this constant, right? All these blue curves over here. To find the specific curve that goes through the point 1, 3, we substitute 3 for f of x. We substitute 1 for both of the x's, and then we're going to solve for that c there on the end. And I think you can see that we end up with 3 equals 2 plus c, and that means c equals 1. Once you find the value of c that you need, you can replace it here and write your function. Our function, f of x, that goes through the point 1, 3 is x squared plus x plus 1, because our c equals 1, right? And our function fulfills that requirement that it goes through the point 1, 3, and it has the derivative of 2x plus 1. So we just solved that initial value problem. We're just finding a function, and there's no plus c in our answer. It's just the function. Okay, so these problems are pretty straightforward. You do the antiderivative, you plug in the initial conditions, and then you solve for c. When you're all done, make sure you write out the function like we did down here. Now let's look at an application where there's context. We'll steal an application from physics that we worked on earlier in the semester. So here we have an application. It's about a type of train, a magnetic levitation train, a maglev. The velocity in feet per second of this train is v of t equals 0.2 t plus 3, and that applies for the interval of t is 0 to 120 seconds. At time t equals 0, the train's in the station. What we mean by that is it hasn't gone anywhere, so its position is 0. So that's essentially them telling us that the point that we want our function to go through is 0, 0. So when we solve for c, we'll use those conditions. We're asked to find the function, right, giving the position of the maglev at time t, assuming that motion takes place along a straight track. Now the reason they're telling us that is because when we studied particle motion, we were moving along a number line. So we're assuming that our track behaves like the number line. Okay, so remember that velocity is the derivative of position. So this thing here is really a derivative, right? V of t equals 0.2 t plus 3. That's a derivative. If you want to find the position function, you do the antiderivative to get s of t. Remember, we use s of t for position. So we'll do the antiderivative. We've got this 0.2 t. Don't panic. You get the 0.2 out of the way, because that's a constant multiple. And the derivative of t is just t squared over 2. We'll clean that up in a minute. Then we have our plus sign. Then we do the derivative of the constant 3, which we know is just 3x. And then don't forget, we're sticking a plus c on the end of this thing. Okay, now let's clean it up a little bit. S of t equals 0.2, which is 1/5, divided by 2 is 1/10. So this is going to be 0.1 t squared plus 3, oh, I'm sorry, this should say t, not x. The derivative of 3 for this function is 3t. Our variable is t, not x. And then remember, we've got that plus c hanging around out there. However, when we plug in our initial condition of 0, 0, right, we stick 0 for s of t, and then we're going to put zeros in for t, we find out that c, in fact, also equals 0, because 0 times itself is 0, times 0.1 is 0, plus 3 times 0 is still 0. These are all zeros. And so we're going to find out that c equals 0. So our final position function is s of t equals 0.1 t squared plus 3t. And that is our final function that they asked us to find. All they asked us was to find the position function, which we did. Sometimes the problems say, okay, now that you have your function, tell me where the train is at a certain point in time, like t equals 100. And you'd plug 100 into this formula to figure out where the train is. But this problem didn't ask for that, so we won't do that right now. Okay, so this is just a brief introduction to these initial value problems. Essentially, you're just doing the antiderivative, but then you're plugging in an initial condition to solve for c. When we get to these word problems, sometimes that initial condition is hidden in the language, right? When they say at t equals 0, the train is at the station, what they're telling us is that it's at position 0. It hasn't gone anywhere yet. So if you have trouble with that, you know where to find me. But in the meantime, good luck working on these problems and take care.